seats, we're going to get started. If everybody can have their seats, we'll get started. Good evening, everyone, and thank you for joining us for our April public event. We are very happy to have with us tonight Clémence Fontanive from the University of Montreal and the Institute for Research on Exoplanets. Now, before we get into our event itself, we are co-hosting tonight with the Dawson Astronomical Society, and George over here is one of our co-execs of the society.
Hello, everyone. So welcome. Thank you very much for coming. We're very honored to have all of you here today with us. I've had the honor to organize this event in collaboration with the RASC, the RASC, as well with my executives, who not all of them could be here, but we have Liam, Executive Secretary, and Nick, our Elections Officer. My co-president, Caleb, could not make it, unfortunately, today, but he is with us in our hearts. So
no, it means Caleb has to do all the paperwork after filing all the reports and everything, right?
Yeah. So yeah, we're very happy to have you here.
Awesome. So this is the first of the astronomy events that we are holding here at Dawson. So I want to tell you a little bit about who the RASC Montreal Center are, for those of you who are here for one of our events for the first time. But there's not working. Oh, it's because you're. Just be 1 moment.
Okay.
That's better.
Is it? Test. Is it heard from the speaker?
Can you hear from the speaker, or is this loud enough? We're okay?
I can hear you.
It's okay. Okay, we're good. Okay.
Good.
So we are on Indigenous lands that are unceded territory, and we acknowledge that not just for their taking care of the lands and the waters, but also the fact that we share the night sky and all of our observations of the night sky with the local First Nations, as well as ancient and Indigenous cultures all over the world. And one place where we can look at that is actually to look at the moon of the month and try to understand the way in which our naming of the moon matches what we see within nature. So an example for right now is we have what's called the pink moon, the full moon that's coming up tomorrow. When you go to look at the full moon tomorrow, it's not going to look pink. The reason why it's referred to as the pink moon is because of the phlox flower, which in the eastern part of Canada kind of covers the ground and really blooms right in that first month after the spring equinox, when the ground is first starting to warm up, when the rains are coming. That pink flower is their first indication that the ground itself is now fertile and ready for planting for the spring season. But what we see in the moon changes so much from month to month, from year to year, and how we see it. So over the winter, we've constantly been referring to the moon as the Great Spirit Moon, or the Large Moon, or the Chief Moon, because it goes so high up in our altitude and is up for so long in our long winter nights. But right now, this full moon is going to be up for just less than 12 hours of the day. We're just past that spring equinox. And in fact, we're at a micro moon, which is slightly smaller than the normal average size of a full moon. So we no longer refer to it by those spirit names, by those ideas of how it kind of gives us reflection and gives us a reason to keep going through those long winter months. So the RASC in Canada is 30 centers across the country. It's the largest single hobbyist organization for astronomy in Canada. And our Montreal Center is more than 100 years old. Our mandate, in addition to sharing the night sky with each other and with other interested hobbyists, is outreach and education. And today's event is one that falls along those lines. So at the end of the talk, please do go to the back, help yourself to some of the outreach materials that we have. We have star finders that help you to identify what's in the night sky at different times of the year. And we have moon gazers guides which help you identify those most prominent features in the moon. We have them in both English and French. We also have our Montreal Center facilities that our members get to take advantage of. We have an incredible observatory at the Morgan Arboretum in the West Island, which is the darkest skies on Montreal Island. And we will be running a few events there that I'm going to tell you about in a few moments. We also have a dark sky site closer to the US border where we have a 16-inch telescope that members can use. The observatory telescope, we have a guided observation night on occasion, and then members can ask to be trained to use the observatory telescope as well. We do observing events and workshops, and I'll tell you about a workshop in a few moments. And then we have a library collection that is hosted at John Abbott College, and it's currently in the midst of a move in location. And so if you want to see the old location and then come and help us celebrate the new location, that's going to happen over the next couple of months. And then these public events, like what we're doing tonight, are events that we hold throughout the year, at least one a month. And it's to bring you either the night sky and an observing event, or highlight some of the amazing research that we have happening here in the Montreal area. Because we really are blessed in the Montreal area to be a haven of space research and space sciences. The other thing I want to mention for our Montreal Center, which kind of makes us proud and makes us a little bit special, is there used to be a magazine in Canada to share the night sky called Sky News. And Sky News folded just over a year ago now. And since it folded, our Montreal Center newsletter, Skyward, is now shared for all RASC members across the entire country. So we now have our astronomy adventures, our images, our stories shared across the entire country. Our members events that I mentioned to you, we have a workshop series in astrophotography that we started in the fall and we've continued through the winter. David Schumann, our vice president, has been organizing these. And our last one is this coming Wednesday. And it's at John Abbott College. And it is a members event. But if you're considering trying out a membership, coming to one of our members events as one of our guests is a great way to do it. If you come this Wednesday, you get to learn about astrophotography, taking those images of the night sky and learning how to process them. We also have our library nights monthly. We just had our last one this past Wednesday. And during the last one, we also had a talk about one of our observing certificates. And one of our observing certificate awardees is here in the audience who observed 55 different items in the night sky over this last year. In May, we're going to have our final library night in our current location. And then in June, we're going to have moved to a new location, still at John Abbott College, but a different room dynamic with a little bit more of an intimate setting and a much more comfortable chairs. So we're looking forward to that. We also have Zoom overviews of what's coming up in the night sky during our Wednesday Zoom clubhouses. And if weather allows, we're going to be starting our Saturday observing again, where we go out either to the Morgan Arboretum or to dark skies to get to take advantage of some night skies. And Santiago Lopez at the back is our observing activities director, and he runs our Saturday observing events. Now, our upcoming public events that I want to invite you to is we have a lyric meteor shower event coming up on Wednesday, April 23rd at the Morgan Arboretum. This is a free public event. We have a short talk from one of our former John Abbott astronomy students. Lily, she's going to be giving us a talk on the history of the lyrids themselves, also what meteor showers are and how you might try to observe them. And then if weather is good, we're going to go out on the field and try to enjoy nature's fireworks. And then on Saturday, May 3rd, we get to celebrate International Astronomy Day with the entire country. We're We're gonna have our own event at John Abbott College, including a talk on chasing auroras from one of our members, Russell Freilich, who went chasing them in Churchill, Manitoba, just a few weeks ago during the spring equinox season. And we're going to also be out doing observing on the field that night and joining a live stream for the entire country that is going to be hosted from the David Dunlop Observatory in Toronto, where we have Canada's largest telescope, a 74-inch telescope. That was the very first observational evidence found of the black hole at the center of our galaxy. So we're going to be trying to highlight a little bit of the history of astronomy in Canada during that live stream. Now for tonight, we're going to be getting to learn about an area that we started to focus on a little bit the last couple of years here at the Montreal Center, which is brown dwarfs, which are kind of this missing link between exoplanets and star formation. But before we get to that, we are privileged this time around, like we've been in many of our public talks lately, to have joining us from Arizona, our honorary president, David Levy. Now, David Levy might be a name some of you recognize. He's a comet hunter extraordinaire. If you were around in the 90s, which some of us looking a little bit older were, or if you've been studying what happened when the comet Shoemaker-Levy 9 collided with Jupiter, the Levy and Shoemaker-Levy 9 is David Levy, who's joining us here from Arizona, and he always starts us off with a literary reference and a welcome. So, David, over to you.
Thank you. I hope that you can hear me. Bonjour, mesdames et messieurs, et bienvenue à la Société Royale Astronomique de Canada.
Hold on one second, David, we're just gonna increase the volume, just one sec.
Are you able to hear me?
Just give us a few moments.
Yeah, because I'm having difficulty hearing you. Well, let me just try and keep it short.
We can hear you very well.
This is probably the most beautiful set of lines ever to touch paper in the English language. It was written by Thomas Gray in 1751, and he talks about darkness. And I believe that even he wanted to represent darkness as being something very depressing and cold. But I would like to interpret it as the darkness that we see every night when the night sky appears, the sun sets and the stars appear. The curfew tolls the knell of parting day. The lowing herd winds slowly o'er the lea. The plowman homeward plods his weary way and leaves the world to darkness and to me. And I do have another poem I'd like to share with you. It is by Hannah Semesh, and it's something that is very personal to me. It's called Yesh Koravim. There are stars up above, so far away, we only see their light long, long after the star itself is gone. And so it is with people that we loved. Their memories keep shining ever brightly till their time with us is done. But the stars that light up the darkest night, these are the lights that guide us. As we live our days, these are the ways we remember. Thank you very much for letting me be a part of tonight.
Thank you. So without further ado, you've heard enough from me. Let's turn it over to Clémence. Yep.
Okay, so hi everyone. Thank you so much for the invitation to give you a talk tonight. I'm not very good at speaking loudly, so if you can't really at some point, just completely shout at me to remind me to speak a bit louder. I'm really pleased to tell you about the object that I study in my research in astronomy, which are these brown dwarfs. So usually people don't really know what they are, like we don't really speak about brown dwarfs that much in the media. So can I just get a show of hands, like who's heard about brown dwarfs? People, okay, that's much better than usual. You're going to make proud of me. Cool. So yeah, I'm going to try to give you a bit of an overview of what they are, why I think they're interesting, where they come from, and how we can study them and search for them. Right, so we all know usually what a star is. The one in our solar system is the sun. We're familiar with this. Typically, most people are also pretty familiar with what planets are. Exoplanets are things that orbit themselves outside of our solar system. And in our solar system, we don't actually have anything between our sun and our biggest planet, which is Jupiter. But in the rest of our galaxy, there is actually a whole family of astronomical objects that is filling this gap between the smaller stars and the biggest planets. And I told it before, but it's ground dwarfs. So ground dwarfs are basically these intermediate objects between the small stars and the biggest planets. And the distinction that we use as boundaries between these different categories of objects is basically based on the nuclear fusion that is happening in the core of these objects. So all stars, so exactly like our sun, are able to undergo hydrogen fusion in their core. So in the heart of our sun, it's burning hydrogen, and that's providing it with a source of internal energy that can make the sun burn for billions and billions of years and stay at the same temperature for billions of years. At a certain mass or temperature limits, that fusion can no longer happen. So if you become too cold or too low mass, that fusion is not able to take place. And that happens at roughly 80 times the mass of Jupiter, or by about 8% the mass of the sun. So if you go below that, there's no hydrogen burning, and you end up with a ground dwarf instead of a star. So that's the key distinction between stars and ground dwarfs. It's based on this ability to fuse or not hydrogen. And then kind of as a symmetry with that upper mass limit that we have for ground dwarfs, the distinction between ground dwarfs and planets or exoplanets is based on the ability to fuse with deuterium, which is heavy hydrogen. And that happens at about 13 times the mass of Jupiter. So we consider that anything below 13 times Jupiter is a planet. Anything between that and 80 times the mass of Jupiter is a ground dwarf, and anything above that becomes a star. So unfortunately, because this definition of ground dwarfs is based on its inability to do something, they got the very unlucky nickname of being failed stars. I think this is a really unfair nickname. They're awesome for so many reasons. They're not failed anything. So if there's one thing to remember from my talk tonight, it's this slide number one. Okay, they're not failed stars. You can call them overachieving planets if you want. All right. So a bit of history on ground dwarfs. So ground dwarfs were actually predicted in the 1960s. That was purely theoretical. It took years before we finally observed them. But in the 60s, Shiv Kumar, who was an Indian astrophysicist, predicted theoretically that there should be things that form like stars, but never become big and bright enough for us to see them. So that they should be these like star-like things that we're just unable to see because they're too dim in the sky. So he initially called them black dwarfs. The name didn't stick because we now attribute this to something else. So the sun is going to become in billions and billions and billions of years. It's going to become a white dwarf and then fade to what we will call black dwarfs. So that name of black dwarf could not be used for these objects that he theoretically predicted. And then in the 1970s, people started to think that these little star-like things that were invisible might be the answer to the missing mass problem. So the missing mass problem is this idea that when we look at all the mass of all the stars in our galaxy and their rotation speed around the center of our galaxy, they're not going fast enough. There's something that's not adding up. If we look at the laws of gravity, between the mass that we're seeing and the speed of these stars around the center of the galaxy, there's missing mass to explain their rotation speed. So that's what we call the missing mass problem. And because we had theoretically predicted the existence of these really small things that we can't detect that are invisible, some people started to predict that maybe that was the answer to this missing mass in the galaxy. So it turns out that ground dwarfs do exist, but they're not the answer to that problem. They're way too low mass, so even if they're super numerous, they can't make up for this. The answer to that question is dark matter. And then we had to wait until the late 1980s to finally have the first ground dwarf candidate detection. So it's the object that you see here in red. It's orbiting this thing here, which is a white dwarf. So that's the exposed part of the dead star. So our sun will evolve to this in about 4 or 5 billion years. And the little brown dwarf is orbiting around this dead stellar remnant. Unfortunately for this guy, it remains a first round of candidate, but wasn't the first one to be confirmed. It was the very first one that was discovered, so its classification was a bit ambiguous for a while, and it wasn't confirmed as a brown dwarf until other things had been confirmed as brown dwarfs. So it just technically was like first candidate, which is better than nothing. And then it's in 1995 that we finally have the first confirmation of the detection of a brown dwarf. And there were actually 2 that were announced in the same year, within a few weeks. So the first one is also orbiting a star, so just like the candidate before. So it's a little dot that you can see here. So this image on the left is from a ground-based telescope in California. This image here is from the Hubble Space Telescope. And it's orbiting a star that looks a bit like our sun, and going around it in an orbit of several decades. It's quite far out from its star. And then the second object, the second brown dwarf that was confirmed roughly like a month after this one, is actually what we call a free-floating brown dwarf. So this one is not orbiting around the star. It's just wandering alone in space, minding its own business and floating through space by itself. So that was already a really cool year, not just because we finally confirmed these things that had been predicted for several decades, but we actually realized that they can exist in several configurations and not just as big planets around stars. Okay, so let's come back to this classification thing. So as I said, the distinction between brown dwarfs and stars and planets is based on this ability to fuse hydrogen and deuterium, and that roughly gives us mass limits for these objects. So we kind of decided on definitions that are based on mass. That's a bit stupid because it's really hard to measure mass for most of these objects. So we have categories of objects for which we need to know the mass, to know where they belong, but we can't actually measure that very well. And the main reason for that, I'm going to walk you through this. So it's that this lack of hydrogen burning actually means that the evolution of brown dwarfs is very, very, very different from the evolution of a star. So what we're seeing here is each line corresponds to an object of a given mass. So we're starting in blue at the top with no mass stars, so about 20% the mass of the sun. And then as we go down, in purple we have brown dwarfs, and then in red we have giant planets. Okay, so each line shows a specific mass. And then what I'm showing here is how the temperature of these different masses of objects evolves over time. So we're starting at 1 million years here, 10 million years, 100 million years, 1 billion years, and 10 billion years. So I'm going to look at the evolution of the temperatures of these objects. So if we start at the top and we take a low mass star, that's what its temperature is going to evolve over the years. So at the beginning, the mechanisms that formed it released a lot of energy, so it's quite hot. So it loses a tiny bit in temperature at the very beginning of its life, but then for billions and billions of years, it's able to remain at a constant temperature. So that's exactly what our sun is doing. It's been shining at the same temperature, same brightness for billions of years, because it's able to do this hydrogen treatment. Now, if you look at a brown dwarf, it's going to look very, very different. It does this. So initially, it's able to remain roughly at a constant temperature because it's doing this deuterium burning. But then that's over pretty rapidly in like maybe 10 million years. And then for billions and billions and billions of years, all the brown dwarf is going to do is cool down. So the fate of the brown dwarf is to spend its entire lifetime getting fainter and dimmer and colder. And then if you look at the giant planets, it's even worse. It never even gets a chance to stay stable. It just cools down from the moment that it's formed. And that leads to something that's really different between like studying stars and studying brown dwarfs or giant planets, which is that for a star, if you can measure its temperature, no matter its age, you can get a pretty good idea of its mass. Like if you see how bright it is in the sky, that will tell you like which one of these lines you're looking at, like basically measuring its temperature. And you can see that if I can measure where on this y-axis I am, no matter the age, except for maybe in the very beginning, if it's super young, I can tell on which of these lines fall, and that gives me the mass of the star. That's not the case for ground dwarf. You can see that for ground dwarf, this is okay, there's a line going to the star. If I measure a luminosity or temperature that falls like along this line that you probably see here, if I don't know the mass of that system, I can't know. If I don't know the age, I can't know the mass, right? Because the same brightness or the same temperature, if it's something that's really young, it's going to be like a 5 Jupiter mass object. If it's a bit older, it might be like 30 Jupiter mass object. And if it's really old, it might be like just at the limit of being a star. So that actually makes ground dwarf studies in astrophysics a lot harder than stellar physics. So to go back to these, instead of using these mass boundaries that we kind of arbitrarily decided on, we're going to make our life easier and think about things in terms of temperature itself, because this is something that we can measure. So instead of thinking about things as stars, ground dwarfs, and exoplanets, I prefer to think about things as a continuous temperature sequence. So where an M dwarf can be either the smallest stars that exist, which are the most numerous ones in our galaxy, or they can be the hottest type of ground dwarfs. And then as we go down in temperature, we have what we call the L-type ground dwarfs. So these are really, really cloudy. They have very dusty atmospheres. And then we have the T dwarfs, have a lot of methane in them. And then finally, the Y dwarfs are the very, very coldest objects that we know. And the coldest one that we know is about -20 Celsius in temperature. So it's about Montreal in January. I could never do that joke so these are the very coldest objects that we know. They have atmospheres that really look like Jupiter. We see ammonia, we see clouds, we see weather patterns in them. But they're really interesting because they provide like exo-Jupiter analogs. And just to quickly go back to this spot that we were looking at, these different spectral classes that I showed you roughly correspond to this. So as I said, an M dwarf can be the low mass star or the hottest ground dwarfs. And then we have these LT and Y sequences. And basically what this plot tells us is that ground dwarfs evolve through these spectral classes. So it's not like it's going to be born an L dwarf that has a dusty atmosphere and that's going to be what it's going to look like forever. If it's born an L dwarf, it's going to be like this at the beginning, and then it's going to cool down and start, the clouds are going to dissipate and it's going to start looking like a spotty T dwarf with a lot of methane, and then it's going to cool down to something that looks like Jupiter. So these ground dwarfs are continuously evolving with time. So their atmospheres are continuously changing, obviously not on the lifetime of our observations. We're talking about millions of billions of years. But unlike a star, they are continuously evolving and their appearances are continuously changing. Okay, so now I want to talk a bit about what that means in terms of their brightness or where in terms of wavelengths we should look for them, like what sort of telescopes we should be using to detect them. So this plot here is showing the brightness of star-like objects as a function of their temperatures. So we're looking at how bright something is as a function of wavelength. And we have really, really bright stars that are going to be like that top curve over here. So it's going to shine at blue wavelengths, so mostly in like UV radiation. It's going to be really hot and very bright. And then the yellow curve is the temperature of our sun. So you can see that it keeps exactly where the visible light is. It's not a coincidence that our eyes develop to see at visible wavelengths. That's because where our sun is shining the most. Okay, evolution displays pretty well. The sun mostly emits at these wavelengths, so we're able to be able to see exactly at these wavelengths. And then the smallest stars, like these small M-dwarf stars, will be roughly that temperature, so they're going to shine slightly at more redder infrared wavelengths. And then these curves are what we care about for ground dwarfs. So you can see that they no longer emit anything in the visible light. So even if there was one not far from the solar system, you wouldn't be able to see it with the naked eyes, or even through a small telescope, just because they don't actually emit anything at these wavelengths. And you have to move to the near or mid-infrared to have a chance to detect something that is visible. Yeah, infrared. That's what we need to do. Okay, and so curves that I showed here are what we call a black body spectrum, so it's kind of like an ideal astronomical body that perfectly absorbs at full wavelengths. Obviously, things don't look as nice as this when we look at the spectrum of objects in the sky. For stars, it's not a bad approximation. So here is the spectrum. So again, how bright an object is at different wavelengths. For an M-dwarf star, so you can see that the blue curve is this black body spectrum at that temperature, and then in black is the actual spectrum of the object. So what you can see with the spectrum is that if there's molecules in this atmosphere, some of the light is going to be emitted or absorbed. So all of these little bits that you can see here tell us about the composition of the atmosphere. But for a star, we're not too far from this black body spectrum at this nice curve. But as we go down in temperature into the ground dwarf regime, things start getting very, very messy. So you can see that it still roughly follows the shape of this black body spectrum, I know in terms of where the peak is. But we start having these like really big dips everywhere. If I keep going down in temperature, the same thing happens. So you can see that it deviates more and more from this, which makes studying them more and more complicated as we go down in mass. But it also makes them more and more interesting because it means that there's so much happening in these atmospheres. And the idea is that they're so cold that atoms don't like to stay apart and they get together to form molecules. So that's why we end up with methane, ammonia, water vapor, and all of these things in these atmospheres that are creating all these features that you see everywhere. And in particular, I was mentioning earlier that the very, very coldest ground dwarfs are particularly interesting because they look like exoplanets like Jupiter. And this is what this is showing. So at the bottom here is the infrared spectrum of Jupiter. So similar to what I was showing you before, lots of dips because there's tons of different molecules that are absorbing light at different wavelengths. And then above is the spectrum of a very cold T-dwarf, so about a few hundred degrees warmer than Jupiter. And you can see that compared to these nice black body curves we had before, these are pretty similar. So we can really use these ground dwarfs to study Jupiter analogs outside our solar system, which is quite cool. Ideally, we would want to find a Jupiter around the star to have a real analog to Jupiter. But if it's orbiting around the star, it makes it really hard to study its atmosphere because then our telescopes are completely blinded by the host star. So if you have a free-floating little T or Y dwarf that's really cold, then we just need to point our telescope at it, and there's nothing in our way to study its atmosphere. So these are the best things out there if we want to look at Jupiter-like things in the rest of our galaxy. And in particular, you probably have heard about the James Webb Space Telescope. It's doing so great to study these ground dwarf atmospheres. And what I'm showing you here is the very first James Webb spectrum that we obtained of the cold ground dwarf. And the reason why Webb is so cool for this is because it really looks at these wavelengths, which are the infrared, mid-infrared wavelengths. For comparison, the best thing we could do for these objects before were the Hubble Space Telescope. Hubble only looks at the mid-infrared, so actually Hubble was only able to see these little bits here. So you can see that most of the light emitted by these objects comes out at much redder infrared wavelengths that we could never see with Hubble. Like Hubble was just limited to these three little emission peaks here. So with Webb, we can finally look at a lot more of what's going on in these atmospheres, and there's some super cool results that have come out in the last couple of years. People have detected auroras in these, which I think is so exciting.
So a quick question.
Yeah.
What's the vertical axis? The variable, the vertical axis?
That's the flux in milli-Janskis. Normalized by rate.
What's millijoules? What's that?
It's Janskis.
Janskis.
Yeah, sorry. Yeah, it's the flux normalized by wavelength. Yes.
Just a very basic question about burning hydrogen versus burning deuterium.
Yes.
Can you explain burning deuterium?
It works in a similar way. So deuterium is like this heavy hydrogen, so you just add a neutron in the atom, which for some reason makes the temperature at which it can fuse lower.
So instead of making helium. Deuterium?
Yes, exactly. That's right.
It's we saw the curve where a low mass star, the difference between a really big brown dwarf and a really like a low mass star do there exist low mass stars that just kind of like fizzle out and then just go to?
So that would be more the other way around. It would be a brown dwarf that initially is able to do a bit of fusion because again, there's so much energy when these things are born. So it might be hot enough initially to try to burn some hydrogen at the beginning of its life, but then it goes back to what it's meant to be, and it becomes a brown dwarf and breaks down forever.
Thank you.
Yeah.
Why is it called a brown dwarf?
Oh yeah, I completely missed that. I started my story with the black hole. Thank you. Okay, the answer is a bit stupid. So basically, we didn't call it a black hole because that was already taken for something else. Because of everything I showed you, like how it shines mostly in the infrared, that means we can't really define it by the color we would see by eye, right? Because it doesn't actually shine at visible wavelengths. Red is already taken by the lowest mass stars, we call them red dwarfs. So then people were like, well, it would probably look something like magenta-ish, but magenta-ish dwarf is not a good term. So then they just decided to go for something that would be in between red and black, and they landed on brown.
If that was like a brown dwarf, but let's say it was lit up by a regular white star as a companion.
Yes.
I know that they emit in the infrared, but would we see, like when we look at Jupiter, it's reflecting the light from our sun?
Yeah.
Because of all the clouds and everything, would that kind of look like a Jupiter with the different clouds and the belts and everything? In the visible light, like if it was
Yes.
reflecting.
Yes, so at the moment, we don't really have the technology to observe these sort of things in reflected light.
Yeah.
But it would look very much like Jupiter, and we are currently developing next generation of telescopes to try and do that.
Like the dwarf.
Yes, exactly. So
Okay.
that's the goal of these telescopes, to observe these like super Jupiters around stars within their reflected sunlight
Yeah.
instead of in their own glow in the infrared.
Okay.
And then it would probably look very similar, but it does what we expect from the physics and chemistry you understand, it should look very similar to Jupiter. Any more questions to try and on? Yes.
If you could rename brown dwarfs for something more descriptive, what would you call them?
So,
Let's say you're changing physics as of today. What do you call them?
no pressure.
Failed start.
I like the overachieving planets nickname. I think I'm gonna stick with that. No, I mean, in terms of colors, like I said, we didn't really have a color that we've defined because we define everything based on what we see and it wouldn't shine at visible wavelengths. Magenta is probably closer to the truth than brown. Pink, yeah. Pink, well,
I have a question.
Yeah.
You'll see more of the spectrum that you see of web. Are you missing some information? Because it can only go.
Yes, so you can see that we're probably still missing some flux over here, but it's still a lot higher here than anything we're doing with HST over there. We don't currently have like a space telescope looking at this. We do have some things that can look at longer wavelengths, but they're not spectrographs, so we can just get an image and measure the total flux over some wavelengths, but we don't have the full spectrum. But I'm sure there's a lot going on here. The interesting things like that we get from looking at the spectrum with different wavelengths is that basically looking at different wavelengths means looking at different depth in the atmosphere. So when I'm looking at these little emission peaks here with HST, I'm looking like really deep in the really high in the atmosphere. And then with web, we can actually like look through the dusty upper atmospheres and see what's happening in the lower layers of the atmosphere. So if you want to get a full idea of what's going on in like the 3D dimension of the atmosphere, you need to get an idea of everything that's going on, and we probably are missing some interesting stuff out there. And then obviously improving the resolution as well. Like this looks really cool compared to what we had before. But if you zoom in on this, it's still going to look very much like a step function. And we could be missing some like very interesting like emission or absorption line of different molecules or chemical elements, just because we don't have the resolution to detect those.
How far away is it closest? One you can actually,
The closest ground dwarf to us
excuse me,
is the question. The closest ground dwarf to us.
I just wonder how far away is the closest one that you've been able to observe so far? This would distance be a limiting factor.
Distance is a big limiting factor, yes, just because they're already so faint that if you put it too far out, the light doesn't even reach us. The closest one to us is about 6 light years. It's actually very close, yeah. I'm excited about it. This one. In the perfect condition. Yeah, so for the next part of the talk, I wanted to talk a bit about how we search for these. Because based on what I've told you so far, it's not looking super promising to find them, right? Like I told you that they're incredibly faint. So we're talking thousands to hundreds of thousands times fainter than the sun, or far like the sun. Because they're so cold, that means that they mostly shine in the infrared, so we need really powerful telescopes at the infrared wavelengths. And there's this added difficulty that they get dimmer and dimmer over their lifetime. So you have a better chance of catching it when it's still young and bright, and then your chances of actually detecting a ground dwarf just gets smaller and smaller with time. But we're still finding them, and we've made good progress in the last couple of decades. So you probably have heard about the Proxima Centauri and Alpha Centauri star, so it's the closest stellar system to us. The next one is Barnard star, which is at about 6 light years. And then the next 2 systems closest to our solar system are actually ground dwarfs. So the third and fourth closest system to the solar system are made of ground dwarfs. So the first one is actually a binary system. So it's made of 2 ground dwarfs that are orbiting around each other. There's no star in the system, just 2 ground dwarfs in a binary system. And then the fourth one, this guy here, which is called Y0855, that's actually the very coldest ground dwarf that has ever been discovered to date. So it's the one that's about -20 Celsius for the surface temperature of its atmosphere. So yeah, and the thing to highlight in this is the discovery year of these guys. So they right at our doorstep. They're literally like the third and fourth closest system to us. I'm sure you've all looked at the night sky, just with the naked eye, you can see thousands of things out there. But it took until 2013 or 2014 for us to realize that these ground dwarfs were just right there. And that's because it's so hard to detect them. And because we needed really, really powerful infrared telescopes to actually be able to detect them, even though they were right there all along. But still, we're making progress, and we now know about around 4,000 free-floating ground dwarfs. So most of the ones we've discovered so far are not orbiting around stars, they're actually rogue wanderers in space. But the numbers are coming up. And based on the ones that we have detected, we can also estimate the ones that we're not able to detect. And based on that, we think that there would be somewhere between 20 and 100 billion in the galaxy, which would be roughly like between 1 and 5 and 1 and 2 from the number of stars in the galaxy. So there's big errors, but they're still numerous. So that means that we can't neglect them. Like if you want to understand everything that's going on in our galaxy, we do need to care about them. Okay, so I'm going to talk a bit about different ways that we search for them and how we detected the majority of these guys. So I showed this image earlier. That was the very first ground dwarf discovered, the one that was found around the star. It's called B59b. You can see that in that place, it wasn't too hard to see it, right? Like I didn't have to do any fancy image processing for it to pop out. Like if it had been a lot closer in, it would have been lost in the glow of the star over there. But it was far out enough that this one was pretty straightforward to see. That's not always the case, and actually in most cases, it's going to be a lot harder than that. So for example, in this image, this is a much brighter star than the sun. That's the one that this ground dwarf is orbiting around. And you might be able to tell that there's like a tiny little dot over there. That's a ground dwarf, but it's a bit hard to tell just like this. So what we have to do is come up with like complex image processing techniques or instruments that are designed to get rid of the light of the star as much as possible, so that we can see if there was a little brown dwarf next to it that was far better. And it looks like this when it goes, which is a much neater detection. So what this image has done here is that we've used what we call a coronagraph. So it's an instrument that basically follows the concept of an eclipse. So the idea is to sort of have the mask in your instrument, and you put the star behind this, so that you block most of the light of the star and can look much closer to the star itself. So just like when you have a full solar eclipse, when the moon passes exactly in front of the sun, you can actually see the atmosphere of the sun, right? You can see the corona, which you won't be able to see when you're normally blinded by the light of the sun. So this is kind of the same idea. We use these coronagraphs like to place the star behind it, and then we do some fancy image processing to get rid of whatever is left around this. And it makes that little dot I was here pop out really nicely, and we can be sure that it is a number. So that's one example. There's quite a lot now. They all look very different depending on the sort of instrument and image processing we have. This one in gray is one that I discovered last year. Yeah, so we've now built up numbers to maybe 50 of these brown dwarfs that have been directly imaged around stars. But it's still a minority of the ones that we know. The vast majority of brown dwarfs are actually these rogue objects. So I mentioned this object here, you might recognize that's the image I showed you before of the first free-floating with this isolated brown dwarf. So I showed you this image before, but actually that's what the original image looked like. Okay, so you have to be able to zoom in so much to be able to see it, right? If I just show you this image, you're never going to be able to tell me that there's this little red dot in the middle. That's a brown dwarf. And that's because the problem with searching for something that's by itself is where do you put the telescope, right? If you're looking for something around a star, your ability to detect something is based on whether there is something around the star, but at least in terms of pointing the telescope at something, you have the starting point, you know where to look. If you're looking for these free-floating objects, where do you start? So there's two main methods that I use for this. They're often used together. The first one is based on colors. So just to come back to what I showed before, we saw before that depending on the temperature of an object, it shines at different wavelengths. So we can use this. We know that a brown dwarf should be much colder than any other star in the galaxy, no matter if they're closer or further away. So what we do is that we use these all-sky surveys. So there's been a bunch of them in the infrared that kind of map the entire sky at different wavelengths. So, for example, we can take like these three bands here that I highlighted, and then we can compare the flux of every object in the same position in the sky between these three wavelengths. And you can see that if something is a star, no matter its temperature, it's going to be brighter in its first band and then dimmer and dimmer. So if I do like a fake color by combining these, it's going to be like almost blue dots. If I have something that has a 1000 Kelvin temperature, it should be brighter in this middle image and then a bit dimmer in the other two. So it should look different, like it has a different fake color when I combine these images. And then really cold brown dwarf or background galaxy is probably going to be very cold and very red and only really pop out in that brightness image. So that's typically what we do. We use these all-site surveys that take images of the same patches of the sky at different wavelengths, and we look for something that has the right relative fluxes in the different wavelengths. And that's an example of a brown dwarf that would shine the most in that green band here. So these are not real colors, it's just kind of made up for us to know in which of the images it was the brightest. And then the second thing that we can do is that because brown dwarfs are quite faint, we're quite limited to the ones that are closest to us when we search for them. So that means that they should be moving quite fast in the sky compared to something that's really far away. Right, so we can use this for this proper motion, so it's the motion of the objects in the sky. And this is an image of the lunar star of brown dwarf. at different epochs, so it's using different cameras, so they're not all the same, but you can see that generally, like a lot of these points like stay still, going from the 90s to about 10 years ago. And then there's this one little thing that is actually moving quite fast in the sky. And that's because it's a foreground object that's moving much faster relative to us. And then if you can confirm that they have these right colors, or can get a spectrum of them, you can confirm that it's a ground ball.
It was like parallax.
No, that's really just a proper motion. Parallax will give us the distance to the object.
Okay.
And that's based on just our motion around the sun.
Okay.
This is really just like everything is moving, has its own motion throughout the galaxy. And the things that are not closer to us will appear to be moving much faster, right? Like if Russian bolt is right in front of you, your head is going to do this. But if it's on the horizon, your head is not going to move. When it does, it's not going to do this. So it's the same idea. We're going to see these foreground ground balls move quite fast in front of us relative to background objects. The next thing that we can do to search for these ground balls is to search for them in binary systems. So I mentioned earlier that this first closest system to us, so the closest ground balls, are actually part of the binary system. So we measured that about maybe 10 or 20% of ground balls are part of binary systems, so with two of them orbiting around each other. So again, it does mean that to find a ground ball around another ground ball, we're going to be limited by this fraction, but it does give us a better starting point than just looking anywhere in the sky. So what we do is that we use different types of telescopes to take an image of a ground ball that has been identified the way that I just showed before. And sometimes it's going to look a bit elongated like this, which it shouldn't be if it's just one object. So then when you have something in image that looks like this, you then observe it with a telescope with an even higher resolution, and you can see that there was actually two ground balls and not this one. And what's really cool with these binary systems is that if they're close enough to each other, we can actually see them move around each other over the years. So we can literally see, this is a couple of examples. The one on the left is that third closest system to us. And by observing these systems over the years, we can actually observe them rotate around each other. And that's particularly interesting scientifically because we can use the laws of gravity to measure the masses of these objects, based on how fast they're orbiting around each other, that can give us the masses. And I was saying before that it's really, really hard to measure masses for ground dwarfs because they're constantly cooling with time and we don't really have a fixed rate based on luminosity. So this is a way to go around this. So binaries are super precious because they allow us to basically scale in mass what we're observing out there. And on binaries, I wanted to highlight the system that was discovered a couple of years ago by a team that I'm part of at the University of Montreal. So this is a James Webb Space Telescope image of a little ground dwarf that is chaos. It's a white dwarf, so the coldest category of these ground dwarfs. So we obtain images at two different wavelengths with Webb. So this one is in the near infrared and this one is in the mid infrared. It's a really, really cold ground dwarf, so it shines more in the mid infrared, which is why it's brighter in this right image, while most other things are comparable, even brighter in the left image. It doesn't look like a binary like this, but we did some more detailed analysis. And without making this too complicated, basically, if we zoom in on that little ground dwarf in this image, it kind of looks something like this. This is very pixelized, but that's the image that we get. And we can model pretty well what the light coming on the detector should look like. So we call this a spread function. We can model what that shape should look like for an object that is single, like if we just receive light from one object. And if we'll find our detector, we should be able to model this well. And if you subtract our model from the observations, and there's a lot of residuals, that tells you that your model isn't very good at fitting what you're seeing. And that's what happened with that object. So we fitted what we should have been seeing if we were getting light from just one ground dwarf, and we ended up with very localized residual up there, which told us that something was going on. So then instead we did a fit of a binary model, so saying, okay, take this one thing I had before, but also add another one and see if it matches better with the observations. And it did much better at subtracting all the lights that we were seeing, which told us that it was a binary. And then the last thing that you can do is to take the same binary model, but only subtract the light of the primary, so that's the binary companion really pops out in your image. And that was super cool because it was the first binary system that was detected around the wide dwarf. So it was the very first time that we detected a binary system where the two objects are basically Jupiter-like things in terms of the atmosphere. Which was super exciting for us. Okay, I don't know how I'm doing the time.
We're good, 8 o'clock, yeah, we're good.
So next I wanted to talk a bit about how these objects form. And that's actually a very big open question in astronomy, which is good for me, because I think that's a job. But stars have their own formation mechanisms, planets have their own formation mechanisms. We don't think that brown dwarfs have their own dedicated formation patterns. Instead, we actually think that most of them form from the end tails of the mechanisms that produce either stars or planets. So we think that they're basically made up of a combination of the low mass products of star formation or the upper mass end of planet formation. Which again makes them complicated to study because two different types of origins. So just to run through some of them. So the idea behind star formation is that there's these big clouds of gas and dust in space. And then they start to gravitationally contract. So that happens over the scale of maybe 1 billion years. And then if some of these regions become dense enough, they fragment, they gravitationally collapse onto themselves and form these little stellar embryos. And then these little embryos keep accreting some of the gas that surround them, and typically they become big enough to be stars, and then they've eaten up all the gas, so the rest of it dissipates, and you end up with like very, very young stars and like a little stellar nursery. It works really well to reproduce the observed population of stars, but it's really hard to explain brown dwarfs with this, at least with most of the models that we have, because basically the minimum mass that you need for these fragments to make little stellar embryos is typically already at the upper end of the brown dwarf masses. So your starting point of your little baby embryo is already almost a star, and then it keeps accreting. So it's really hard to keep these things low mass enough that they're brown dwarfs. So we do think that most brown dwarfs form this way, but we have to sort of twist the usual stellar formation model if we would somehow want them to produce brown dwarfs as well. So there's two main ways to do this. The first one is what we call the ejection scenario, which is probably my favorite one. So I have a little movie here. So what I'm going to play is, so we're going to be seeing the same two things on the left and right panel. The one on the left is in terms of the density of the gas. So you're going to see this gas of cloud and dust evolve. And then on the right is based on the temperature. So it's just because different features that are going to come out in sometimes in the density, sometimes in the temperature scale. So you can see that the cloud is evolving, you start having these little embryos that form. It's like the hottest and densest parts, like sometimes they interact. There's actually another interaction, and then soon one of them is going to be like ejected towards the top and fly off. You see that? And play it again. Okay. So if we zoom out, you then basically see that you have this little embryo that got ejected really early on in its secretion, and it's now left in the part of the cloud where there isn't much material around it. So it's not going to be able to grow much more than this, because it kind of got cut off from the material that they would need to keep becoming a star. So that's one of the scenarios that we have to explain brown dwarf formation. It's through this ejection scenario where stellar embryos get sent out, ejected outside of the gas of cloud, where it would normally be going. And then the second idea that people have is what we call the turbulent fragmentation model. So without going into like technical details, the idea is that if you have a magnetic field in this gas of cloud, it can increase the density, right? And you saw just before that it's only like where you have high densities that this fragmentation happens. So by increasing the density through basically like shock waves that propagates thanks to a magnetic field, it allows you to decrease the threshold that you need for these little embryos to form. So you can have little patches of cloud that collapse onto themselves from a lower mass. And if you can start collapsing things from a smaller mass, you have a higher chance of keeping some of them low mass enough that they're still grounded by the end of that process. Okay, so that was for the stellar formation side. And then the other idea is that planets form around stars, typically in disks, like we see here. So they're kind of like the reservoirs of material that stars have to create planets, to build planets. And sometimes, if something gets bigger than 13 Jupiter masses, then it's going to be a bundle of another star. So there's two dominant planet formation channels. The first one is called the co-accretion model. So this is how we believe that the planets in our solar system form. So the idea is that our sun had this big disk of dust and clouds and gas. And as it cooled down, it became more like rocky. It started forming these little pebbles that gravitationally started accreting onto each other and forming the rocky cores that we have in all the terrestrial planets. And then for those that became big enough, they became then massive enough to create a big atmosphere like Jupiter, Saturn, and all the gaseous planets. So that's the way that the planets in our solar system form. It's really hard to form groundwater with this. Like it could maybe sometimes happen, but actually from what we understand of this mechanism, you could only form really, really big giant planets of groundwater around very, very massive stars that have really huge disks, or around very metal-rich stars, which are not that common. So it could happen, but it's probably not the best pathway to create groundwater through these planet formation channels. Instead, there's another way, which is through the gravitational collapse of the disk. So this whole accretion that I just showed happens once the disk has like cooled down and like the dust can become like little rocky pebbles. But early on in the disk, sometimes it can become gravitationally unstable. And in a similar way to the gas of cloud that we had forming stars, it can collapse into itself and again form these little embryos of giant planets or groundwater. And just on the physics behind this, it's again the mechanism that tends to keep accreting mass. So it's actually better to form, it's more efficient at forming groundwater. So we think that the ones that form around stars probably come from this formation pathway. But again, the simulations that do work are only working with like conditions that may not be super realistic, like it doesn't really match the sort of disk that we observe. So it could work, but we still have some work to do to really be able to explain the problems that we observe through this. Okay, so that brings me to the first summary. So we see that there's two main formation pathways for groundwater, and we've seen that they exist in many different configurations. So let's try to like sort of place them based on this. So we saw that the majority of groundwater are these free floating rogue things that probably form like we saw through stellar mechanisms. So they're like our sun, but just remain small enough that it became a little groundwater that is floating through space by itself. Then we have those that are around stars that probably form in the disk around the host star. And we saw that we have binary systems. Those are probably similar to, they're like miniature versions of star binary systems. So we do think that in most cases, the two components will be in these bell stars, but let's not put them close. But if you can form a binary system where the two things form through a stellar channel, why can't you form a binary system where one of them actually becomes a star and the other one remains a groundwater? Right? So when you see a groundwater around a star, we do think that they probably form like a really big planet, but it could also be that it should have been a stellar binary system and one of them remained a groundwater. So it could also come from a stellar formation channel. And then similarly, when we see a rogue brown dwarf, it could have formed around a star and got ejected from that system. So it initially was orbiting a star, but we no longer see it as orbiting a star. And then it's kind of pushing it, but why not imagine that you could also form two things in that disk that get ejected together? So you observe a binary system that forms like a planet in a disk of a star, but is now composing binary. So that's to say that they exist in all sorts of configurations. We do think that there's multiple origins for these brown dwarfs, but it's actually really hard when you see like a single system to know where it came from, because whatever the configuration, there could be multiple ways to explain it that come from different origins. And the only thing I haven't mentioned on this is potatoes. Yes.
What if there's one form of stellar formation in a binary system with one form of planetary formation?
So
Cross-binary.
you want one of them to have formed like a planet around a star, and then another one to have been a binary companion around the same system.
I guess.
Is
this like if like there could be two planetary formation that are together?
Yeah. It could happen. We do see weird triple systems out there, like they do exist. But yeah, I guess it's just adding additional things onto this diagram. There's like really endless configurations. You could have, we know some system where there's like a Jupiter-like thing around a star, so that one most likely formed like a planet. And it's orbiting quite close, and then really, really far out, there's a massive ground dwarf that is orbiting that system. So it's likely that the planet did form like a planet, but the ground dwarf probably formed like a star, and it's probably like a miniature binary companion, even though there's something else in the system that formed like a planet. We see all sorts of things. It's very messy and very hard to interpret. And the last thing I wanted to discuss in a couple of minutes was the possibility of them hosting planets. That's the one configuration I haven't been talking about. So we do have a couple of examples of systems where there's something with the mass of a planet that orbits something with the mass of a ground dwarf. So these are two examples. So this one, the colors are a bit confusing, but they're both ground dwarf temperature things. This is a ground dwarf of about 25 times the mass of Jupiter, and at about 55 astronomical units around this, so a bit more than the orbit of Pluto. There's something that's only 5 Jupiter masses. So 5 Jupiter masses is below that 13 Jupiter mass deuterium burning units. So according to our definitions, this is a ground dwarf and this is a planet. And then similarly, this is another system that some of my collaborators and I discovered in the Hubble Space Telescope. It's a system again with no star, and the two components are about 15 and 8 times the mass of Jupiter, so super, super small things, and they're separated by 200 astronomical units. So that's like 4 or 5 times the orbit of Pluto, but with no sun in there, just like a few tens of Jupiters. And again, this is just above the limit between planets and ground dwarfs. This is technically in the mass regime of the planets. So we do have these systems. I don't really think about those as a planet around the ground dwarf because the mass ratio between the two is so big that it's more like a miniature, again, binary system, but that's actually pushing things not just in the ground dwarf mass regime, but also in the planet regime. So they're probably more like binary companions. We don't have any detections of anything that really looks like a planet that would have formed around the ground dwarf, but we have reasons to believe that they could form. We just don't have the capabilities to detect them. So the two main reasons to believe this is that we have detected disks around young ground dwarfs. So we know that they do have these reservoirs of material that you need to build and create planets. And then the second good hint is that small M dwarf stars, so that are just above the limit between ground dwarfs and stars, do quite frequently host small rocky planets. And you may have heard about a system called TRAPPIST-1, So this is a very, very small star. So it's about 84 times the mass of Jupiter. And it has 7 small rocky planets within the orbit of Mercury. Okay, so it's a really, really compact system. But it's something like this host star is almost a brown dwarf. It was so close to being a brown dwarf, like 75 or 80 Jupiter masses is the limit. So I actually think of Trappist-1 as a failed brown dwarf. But my point is that the ability to create these planets in the disk around this really tiny star doesn't care about whether the heart of this star is burning hydrogen or not. Right? Like this is what we place as our threshold between what we call a brown dwarf or what we call a star. But the ability to create these planets has nothing to do with whether hydrogen fusion is happening in the core of this star. So if these processes are able to take place around a small star like this, there's no reason to believe that they couldn't happen around a brown dwarf that wouldn't be far from that limit. Maybe we would be pushing it for this to happen around like a 20 Jupiter mass brown dwarf, but around a 60 or 70 Jupiter mass brown dwarf, there's no reason to believe the same things can't happen. The only problem is that to detect these, we are requiring to get quite a bit of light from this star. And the problem is that the brown dwarf that would be just below the threshold for this boundary between stars and brown dwarfs will actually have cooled down over its lifetime. So for the same age of the system, the star is still quite bright, but the brown dwarf has faded so much that we don't get enough light to try to be able to detect these planets. So we're hoping that with next generation telescopes, we're going to be able to start pushing into that. We definitely have reasons to believe that there could be small rocky planets on these. The potential for life would not be great because there's no stability. Right? Like the reason we were able to develop life on Earth is because the sun has remained stable for billions and billions of years. Because these brown dwarfs are constantly cooling down, if it was the equivalent of a host star for a little rocky planet around it, the planet could form, but you wouldn't really have any stable conditions. So it would be really, really tricky for life to be able to develop and be sustainable. But yeah, I'll just leave you with my summary and take any questions. Thank you.
How common within solar systems are brown compared to our situation?
So we don't see them that often.
Okay.
They seem to be a bit of a gap between how often stars have planets. Like we think that roughly there's 1 planet per star on average. Binary systems are quite common, like about 50% of stuff like our sun are typically in binary systems. But we've only found about like 40 or 50 planets, brown dwarfs orbiting stars, while we know like thousands of exoplanets orbiting stars. So they seem to be uncommon, which is probably because they come from like 2 end cells of 2 different mechanisms. So we're kind of looking at the mass regime that's like the depth of the 2 mechanisms creating them.
Of course, I would prefer to be like missing link between like the yellow dwarf of our sun and exoplanet.
Between what, sorry?
A red dwarf. Is it ever a consideration or this link between like our star like our sun and like an exoplanet?
So we do think of it as a missing link in terms of like filling this gap, like the continuity in mass and temperature. Physically, we see them in all sorts of configurations, so they kind of also, like sometimes they act as like the primary host in the system, sometimes they act as like the small planetary secondary. So they are kind of bridging the things that we knew about stellar physics and exoplanets. Yes.
Well, you said there's like 2 methods we theorized that brown dwarfs are formed. So will there be like a difference in the temperatures of the brown stars formed by those 2 different methods?
So in the temperature, yes and no. So because they constantly evolve, temperature is constantly changing. So it's hard to answer that question directly because They may not start with the same temperatures, but it does mean that since they cool down, there will be some big overlap in the temperatures of the objects you create. We do think that the stellar formation mechanisms are a lot more energetic. So things are a lot denser and harder when you form a star. So typically, if you form a grand dwarf through a star-like formation process, it's going to start its life a lot hotter. And then if you form them as a planet in the disk of a star, that's a much colder starting point. But then they will both cool down. So eventually they will reach similar temperatures at some point. Yes.
A couple of slides back, you had a point square function of a binary dwarf system.
Yeah.
So those are ring around it. I'm just really curious, is that a diffraction ring or is that stuff?
Which one do you need?
Well, back or more when you were doing subtraction, pattern subtraction.
Oh, for the binaries,
Yeah.
was it this?
There. So on the leftmost, there's like kind of a ring around your point square. Like the,
Oh, that's part of the PSF.
okay.
That's just the shape of the point square function that we get with web. If you get something really bright enough with web, you typically see these like
Okay.
the six, like the
Yeah.
us. The ground dwarf isn't really warm enough to see this, but kind of see that image. It's some colors down. It's part of the PSF.
What's the most intriguing question?
The most intriguing question.
Yeah.
I think in terms of atmospheres, I didn't really work on atmospheres, but I have some colleagues that believe that they've observed auroras on these, but we've never been able to detect a magnetic field, which you kind of need. So all of the planets in the solar system have been observed to have auroras, but you need the magnetic field and you need the stellar wind, like the sun, coronal ejection for that to happen. If you have an object like a Jupiter that's floating alone in space, you're missing some of these elements, but we do believe that we have seen some auroras. Some of the explanations are quite cool, so like it's also based on the solar system, but we know that some of Jupiter's moons have some auroras that come from interaction with Jupiter's magnetic field, so it's not going to do with the sun. So then the explanation could be that it has a moon itself, like that grand dwarf has a moon, and this is what's creating the aurora that we're detecting, the interaction between the two. It's going to be hard to confirm, but that's the theory that they put forward, which I think is super exciting. Yes.
So based on the model of the formation of the round dwarfs, do we know if they have ever existed in the early universe, or are they just a result of second, third, fourth generation nebulae and star formation?
So there's no reason to believe that they wouldn't have formed earlier on, and it's a bit hard to estimate the ages of these, but we have observed a few grand dwarfs that are particularly metal poor and believed to be really, really old, like almost the age of the universe. And then that would explain why they're so metal poor, because they formed at generations of star formation where there wasn't all these heavy elements that had been created yet. So we do think that they were already forming. There will be the same hurdles in the way of forming them. That's mechanisms that produce them tend to grow different things, but there's no reason.
So the heavy element rich nebula of today's universe is not a contributing factor.
It's not. It changes the compositions of the ones that do form. They will be more metal rich. But in terms of, when I say metal rich, it's what we can observe in the atmosphere. Like we're not really able to probe what's happening in the core, which is where most of the heavy elements would fall. But there's no reason to believe that it changes their ability to form at least.
Just a very good follow-up question. Have we ever observed a spinning round dwarf? Do we know
Yes.
the periods of their?
Yes.
Yeah.
Some of my colleagues in the UK are working on observing the rotation velocity of them. And there's actually some really cool things where they do the same experiment that they did in wavelengths, And I mentioned earlier that using different wavelengths throws different depths in the atmosphere. And if you observe different rotation velocities, that means that you're seeing winds basically that are not rotating at the same speed depending on how up in the atmosphere they are. So that's been observed, yes.
Thank you. Do they have a solid core?
Most likely not. The ones that would have formed through core accretion, yes. But anything that formed through the star formation mechanism or the gravitational collapse of the disk is just gas and dust falling onto itself. So again, it's something that we can't directly probe, but from our understanding of the physics and chemistry, that's the answer for the majority of them.
Shall we take 2 more questions and then we can discuss more during the chat? So there's one here. and one-
Yeah, so you said that, well, it's like, the brown dwarf fuses deuterium very quickly. But fusing deuterium, it also like emits neutrinos. So would it be, is it technically possible to like detect how much a brown dwarf emits neutrinos and therefore like find the age of this brown dwarf, and is such research done?
That's a really good question, and I've never thought about this. I don't know how to detect neutrinos in space. But I'm not sure. But this is
Sounds like a
interesting
PhD, doesn't it? Last question.
If potentially you have a brown dwarf around an older planet, what consequences may there be for the planet? Like,
Sorry, can you say that again? The brown dwarf around.
planet,
Yeah.
like an older planet,
Yeah.
what consequences could it bring to the planet itself? Within over time, since like the ground or holding entered different times, so obviously it will not be essential.
Yeah. Yeah, so it does mean that the heat that the planet is getting from its host is going to be drastically changing over time. It's going to be cooling down, so it means that it will get colder for sure. For me, the major consequence that would have would be on the ability to potentially develop life. Like that would be the main issue that would be associated with this lack of stability. But otherwise, yeah, the main difference is that unlike the planets in our solar system that have been quite stable in terms of the amount of heat and energy we receive from the sun since the formation of the solar system, it will just receive less and less heat over time, so the planet itself will just get colder and colder.
Will it have consequences for the planets like around the planet?
It shouldn't, because the temperature doesn't affect the orbit, like that's just based on gravity and the masses don't change. And you could initially have like the equivalent of an asteroid belt and like start to form a moon, but that happened really early on in the solar system. So it's not over the scales over which this temperature change really matter. I don't think there would be too many differences.
Let's give another round of applause. So, before I call on a couple of thank yous, just a couple of things. Reminder that April 23rd, we have the Lyrids Meteor Shower Night at the Morgan Arboretum at 8 p.m. And on Saturday, May 3rd, we have the International Astronomy Day. And Clémence mentioned that the atmospheres of exoplanets are kind of an interesting topic. And I can tell you now that on Saturday, September 6th, our Townsend keynote speaker for the year is one of her colleagues, Lisa Dang, who's going to be starting her professorship at University of Waterloo, but will come back to give the talk for us at John Abbott College. So you'll see that if you sign up to our RASC Montreal public events list, or if you just look for the posters as they go up all around, pretty much all around West Island, but also at Dawson, hopefully come September, we'll be having the posters up here as well. Now, for our thank yous, I want to call on Maury Portnoff, our RASC Montreal president, as well as Liam, one of the executives here from the Dawson Astronomical Society. And they'll both give some thank yous, and then we'll all get to chat and have some coffee and tea. Voilà.
I'd just like to thank, first of all, Dawson Astronomy Club. First of all, hopefully many events, we'll see you at some of our events. Dawson, I just want to say Dawson's changed since the mid-70s when I was a student. And it's nice to see a really wonderful campus, although we did get lost. But and I want to thank Clémence for a wonderful talk, gave us lots to think about, and hopefully we'll see you at some of our actual observing events.
Once again, thank you for everyone for attending. It really means a lot to us, and thank you for the RASC and Dr. Clémence for the very wonderful talk. You guys are free to stick around and have some snacks, coffee, hot chocolate, and ask Dr. Clémence if you have any more questions about the talk or the RASC folks. They will be in the back. So thank you.